regards to interlinking this form of acetyl-CoA. Where are we going to get more acetyl-CoA? We've already devised we can get it from our carbohydrates. I've already provided you an illustration that you can get acetyl-CoA from fatty acids from utilizing the glycosylate cycle. But how do we normally, as higher organisms, utilize our fatty acids? And we're going to have a look at that today. We're going to look at fatty acid and glycolysis, and also fats and absorption, because this is a key, again, transport system that we need to move these fats into particular organelles and do things. We're also going to see the issue of our triacylglycerols and metabolize those long-chain fatty acids, but also metabolize the glycerol backbone as a form of energy. So we're not wasting anything in regards to our triacylglycerols. We're also going to see the transportation of fatty acids, because they have to be transported selectively and specifically, into the mitochondria. And then we're going to be seeing a reaction called a transesterification, which is a requirement for the movement of those fatty acids into the metabolic pathway within the TCA cycle and within the mitochondria. But also we're going to specifically look at fatty acid oxidation. And we're going to look at a number of different types of fats. We're going to look at those that are saturated, those that are monounsaturated, and those fats that are oxidation based on odd numbers of carbon chains or carbon number in the fatty acid chain. And we're going to specifically look and have to know the process of fatty acid degradation, specifically beta oxidation. I'll also introduce alpha oxidation, but I want you to know the process of beta oxidation. And I love putting questions on the exam in regards to radioisotopes of fatty acids and looking at where they are degrading and what products they are making. So be aware of that when we have a look at the process of fatty acid metabolism. And we'll mostly continue this particular lecture on Tuesday, because I'm not going to finish it all today. So let's have a look at what we're going to be dealing with in regards to fats. So fatty acid catabolism, the breakdown of fats, is a very well-studied area. We see over the years different names given to certain fats. We have the triacylglycerols, the triglycerines, and neutral fats. These are all constituents that are basically utilized in our diets. We have been able to manipulate the genes within animals to either decrease or increase their fatty acid metabolism, as we see here with this transgenic mouse, which unfortunately is putting a lot of much larger and obese compared to its normal counterpart. And we do this specifically to look at the consequences of producing an obese animal and its consequences on its metabolism, on its health. So again, we utilize this and then translate this information to medicine. So that's called translational medicine. So the advantages of fatty acid catabolism is mainly because it's a great fuel storage, like we saw with the sunflower seeds or the cucumber seeds, with the amount of oils they have, which they are going to rely upon to go through the process of germination. Long chain hydrocarbons, we've already been introduced to these. They're highly reduced structures, but we can go through a complete oxidation of these and get enormous amounts of energy, 38,000 kilojoules per gram. So if you think your body weight fat mass index, so there's this BMI index, the amount of fat you have in your body, you can live off, ideally, as I said, 2 to 3 months in regards to maintaining just hydration and utilizing that particular source for an energy. The ideal thing is that it has twice the same weight of carbohydrates or proteins. So again, 1 gram could equal many grams of fats and 1 gram of fat could equal many grams of sugar and many grams of protein. The sad thing is it's also insoluble, so we're going to have some issues regarding transportation. And and it has very limited impact on the osmolarity of the cell, which is great, unlike what we see with individual carbohydrates. It is also, in many ways, chemically inert, meaning it doesn't degrade or break down if it's just kept in a particular structure. So that means we can store large quantities of this and utilize that as an energy source. But we also use this as a protector of organs, particularly in the kidneys, and also in, I think, with the liver, where we see fatty acid deposits in the liver called fatty liver, we can also utilize those particular components in regards to an energy source. So, a bit of a recap: we have even saturated single bonds. So, again, the fatty acid, which has a carboxylic acid and a long alkyl chain. We can have single bonds, so they're saturated. We can then have unsaturated, where we might see a double bond being present. Then we have even polyunsaturated, which has not a single but multiple double bonds. And then we also have fatty acids that are odd in number, meaning remember the naming component is carbon number 1, 2, 3, 4, 5. Remember C18 semicolon 0 or semicolon 1 delta 9. We've got to remember those because they're going to come into play in regards to the fatty acid nomenclature. But also these odd number fatty acids where they might have 15 carbons instead of 16. If we look back in our notes on fatty acids, you will see most of them are even numbered. But we do see some uncommon fatty acids that are odd numbered. And these are mostly seen in plants and marine organisms. So we might be able to metabolize them to a degree, but we're always going to have an uneven product in regards to breaking down constituents of 2 carbons at a time, and then basically leaving us an odd number carbon at the carboxylic acid. But we're going to have a look at that today, or maybe on Tuesday. So we're now in chapter 17, page 649 to 661. So we've covered a lot. If you think about what we have covered throughout the whole text in the lecture series, you'll be amazed at what you've now understood and can apply. So there is some problems with fatty acids, though, because one of the problems is a lot of our enzyme systems require solubilization. So we have to go through a process what we call emulsification. And this is basically where we have to make it some level of accessibility and interact with molecular water. If we need to carry these fats around the body as an energy source to get to the muscle or to the liver or to the big toe, we also have to make sure that they are being carried by additional carrier proteins because, again, they're not soluble. So we're going to have these particular proteins such as alipoproteins, give us this capacity to move those lipids safely through the circulatory system. Now, we also have the stability of the carbon-carbon bond in the long alkyl chain. But the interesting thing is we go through a degradational process where we are basically producing acetyl-CoA, which is soluble. So we're taking basically 2 carbons off this long-chain fatty acid at a time to make acetyl-CoA, as we'll see very shortly, and that is soluble. So we're going to go through oxidational systems called beta oxidation, and it's 4 steps that you need to know and understand. And we're going to see how we degrade these long-chain fatty acids to produce the individual constituents of acetyl-CoA, which is going to be our energy source. Now, just to recap, we have a carboxylic acid, the carbon number 1 position. The carbon number 2 is the neighboring carbon, carbon number 3, and then carbon X. The nomenclature is that the carbon number 2 is also known as the alpha carbon. The 3rd carbon from the carboxylic acid is known as the beta carbon. And the carbon at the very end of the chain, depending whether it's even, odd, long, or short, is known as the omega carbon. So keep these in mind because we're going to be utilizing this nomenclature in regards to its degradation. So we need to ensure that fats are a part of our diet because they are high energy sources. We've talked about, and that we can also store these particular fats in specialized cells which have access to the enzymes for their mobility and their degradation. And also, we can synthesize fats if need be and move those for export using the alipoproteins in the circulatory system. But ultimately, we are going to be degrading these fatty acids in the mitochondria. And that's where the enzymes are all housed in regards to beta oxidation. But as you know as well as I do, there has to be some transport system, some control and mechanism to bring these fatty acids into the mitochondria. And there's going to be some problems in regards to the length and size of these fatty acids, as well as the triacylglycerols. We cannot move triacylglycerols into the mitochondria. They only have to go into as small chain fatty acids. So let's have a quick review, just a second, in regards to acetyl-CoA. We can, via the pyruvate dehydrogenase complex, we can produce acetyl-CoA and by consuming pyruvate. We're going to see fatty acid oxidation now also supplement this pool of acetyl-CoA. Now, acetyl-CoA, we can go through the TCA cycle and fully oxidize it in the bigger picture when we look at the oxidative phosphorylation system and later on to produce carbon dioxide and molecular water. But in this process, we're we're making ATP as well as through glycolysis. Now, acetyl-CoA, depending on what type of organism you are, can also be utilized as a fuel source and a biosynthetic precursor source in plants, where acetyl-CoA mostly in animals is used as a fuel source. So again, depending what you are, you can utilize this particular acetyl-CoA, and that's why we need a large amount of it in plants to produce a lot more different biomolecules. But ultimately, in us, we're taking glycolysis, acetyl-CoA, TCA, oxidizing it, producing carbon dioxide from the TCA cycle, as well as metabolic water from the oxidative phosphorylation system, which we will talk about a little later on and summate everything that we know in regards to the full metabolic process. But today we're focusing on this guy in the supplementation of beta oxidation or omega or alpha oxidation to produce acetyl-CoA. So let's talk about the mobilization of fats first off. So you've eaten your Happy Meal from McDonald's, which is a large fat content in there, and you're basically going to emulsify it, start breaking it down with amylases. So if you think of your saliva is already doing its job in regards to breaking down simple sugars, but nothing's going to start breaking it down until you basically start getting it into the intestines as well. Into the stomach, and then move it to absorption into the intestines, particularly in the small intestines. So in this case, the fats come in, we have the gallbladder, which is going to produce particular bile salts. And these are like soaps. They like emulsify the fats and produce them in smaller globules or smaller vesicles or micelles to allow more greater access and surface area for enzyme attack. So bile salts emulsify the dietary fats in the small intestines. So we basically chopped everything up, hydrolyzed everything. We've absorbed some of the amino acids, but most of the fats are going to come through. They're going to be neutralized by the bicarbonate, by the pancreas, and utilize the gallbladder to provide the bile salts, the emulsifiers, and give you these small micelle constituents. What we're going to see in the intestine, particularly in the small intestine, these lipases, so like the phospholipases we've talked about, to degrade the triacylglycerols to become the glycerol and the individual fatty acids. We're going to get those particular fatty acids and basically get them taken up by now absorption mechanisms in the intestinal mucosa and convert them also into triacylglycerols. So again, we're going to break them down and reconvert them into triacylglycerols for transportation. So once they're in the circulatory system, they're going to be transported into alipoproteins or chylomicrons and allow them to be transported happily into the circulatory system. So again, they've gone from the intestinal GI tract into the capillaries, because they are having a transport capacity. So the chylomicrons have a capacity to move in the circulatory system as well as the lymphatic system. So we have a dual system. We have circulatory and lymphatic. Lymphatic is a capacity to move antibodies as well as we know with fats, where the circulatory system has the capacity to move antibodies, fats, as well as blood around the system, including nutrients. In this case, within the walls of the various blood vessels, there's these lipoprotein lipases, which are going to basically convert and destroy the chylomicrons to give us the triacylglycerol breakdown products of fatty acids and glycerol. Once those free fatty acids are available, they'll be uptaken into particular specialized cells where they can actually also form triacylglycerols again for storage. So they're going to be going into hepatocytes in regards to fat storage, or they can be then also diverted in their free form as free fatty acids to go through beta oxidation and the TCA cycle via the reduction of acetyl-CoA. So fatty acids are oxidized or as fuels or reesterified in forming the triacylglycerols as a storage component. So we don't store free fatty acids. We store triacylglycerols. So again, the constituents that we've talked about in the past. The myocardiocyte, or the heart cells, are very specialized because they actually utilize fatty acids as a preferential energy source over glucose. So in that particular case, we need to make sure that we have a ready supply of these particular free fatty acids circulating in the circulatory system to feed the myocardiocytes. So we talked a little bit about the transport system and this reesterification, degradation, reesterification, depending on what we want to do with those fatty acids. So here's our alipoprotein in regards to this carrier, which is going to be carrying all the triacylglycerols embedded in a membrane, a micelle, so to speak. But in the micelle, we have these particular proteins also ready for the degradation and enzymatic activity of the degradation for the triacylglycerols. So the idea is that we basically have locked away our fatty acids to increase solubilization because the bile salts have allowed us to form these micelles. By having these specialized and compact areas. So when an enzyme comes in, it has a high substrate concentration to increase then basically the degradation of those fatty acids to bring them to their single free fatty acid form. In the process, we can also utilize these as a storage a carrier in the circulatory system by forming these micelles, because we get this level of aggregation and these chylomicrons in regards to their breakdown and become a smaller moiety. And this is where we see these very low density lipids and very high density lipids in regards to the cholesterol lipid concentrations that when you do a metabolic profile in a hospital, you see whether you have these very high or very low density lipids. And as you know, some of these have been correlated specifically to cardiovascular implications, whether you might be at risk of high blood pressure or risk of a heart attack because of the occurrence and abundance of these long chain or high density chain fatty acids that are circulating in the chylomicrons. So again, they become a diagnostic tool in regards to establishing how healthy you are. So I'm going to also introduce to you our hormonal component, our GCPRs, that play also a role in regards to the degradation and mobilization and transportation of fatty acids. So again, we see this interconnectivity that we have experienced in the past regarding the GCPRs and the adenyl cyclase and cyclic AMP. This time, cyclic AMP is going to be an activator for the protein kinase A, to actually mobilize and phosphorylate a hormone sensitive lipase. And this hormone sensitive lipase sits in the cytosol as a non phosphorylated form. Once it's phosphorylated by the enzyme, the protein kinase A, which is stimulated by the cyclic AMP concentrations, which is stimulated by the adenyl cyclase and the GS and the hormone receptor, we're going to see that hormone sensitive lipase come into the lipid droplet, which is the storage area for the triacylglycerols, and do its job as a lipase to basically degrade the fatty acids to allow their movability. So again, removing the triacylglycerol to make them the free fatty acids in the glycerol. The free fatty acids then have the capacity to move through the cytosol and then be taken up by a protein, in this case serum albumin as a protein carrier, to then be moved around in the circulatory system. So I'm going to leave it there, and we'll talk more about fatty acids, their transportation, regulation, and oxidation on Tuesday. Now, we will have the exams back to you, I believe,